Before we start, here is a surprising statistic that we would like to share with you. On average, 52.5% of manufacturing waste is landfilled every year globally. This statistic tells us that there is a great demand to improve processes and make it more efficient when it comes to quality. Which leads me to my next point on how we are using machine learning to make quality predictions in the mining process. Without any further ado, let me introduce you to the team behind this project. We have Gregg, myself Nisarg Patel, Omar Hamdy, and Khurram Shafiq. There are three key things we will cover today about our project. At first, we will look at the problem that exists and how team decided to tackle it. Secondly, we will look closer at our solution, including the data set that we have used and ML models that we came up with. Lastly, we will wrap it up with key findings of our project as well as the next steps on how we plan to move forward. Let's dive into the problem. Here is a picture of iron ore concentrate on the left, and when examined closely, it contains silica in the form of very small rocks. So our problem statement is to essentially predict these silica rocks that is potentially present in the iron ore concentrate. You might wonder how the silica gets separated from the concentrate. So next, I will explain the process of the flotation plant. This diagram shows the high-level process of the flotation plant that uses physical separation process to remove impurities from the iron ore concentrate. You start by inputting the concentrate into the flotation plant. The plant will remove silica and other impurities by physical separation means, and as a result you will have a refined iron ore concentrate. Next, we will look at our dataset and solution aspect. Here is a quick summary of our dataset that was obtained from Kaggle. It's from 2017 and with a usability of 10.0 as the data is fairly clean. Couple of key things to note are highlighted in yellow. Specifically, the data is collected from the machine sensors at every 20 seconds and we have a data from a 6-month range. So we have a good depth and breadth of the data. As you can see from the number of instances, it's a fairly large data set. And after examining the data and the problem, our team came to the conclusion this problem is a supervised regression type problem. After reviewing the data and in the process of preparing the data for ML modeling, our team decided to take two different approaches to see which approach will perform better. Due to the large data set, we decided to create a resample dataset that aggregated the sensor values to every hour from the 20 seconds, which became our approach number 2. Also, a different outlier in detection as well as feature selection methods were used between the two approaches. So after cleaning the dataset, you can see a lot of outliers were detected and removed, and hence the data size was also reduced. Now we are ready to create an ML model from the dataset. This diagram outlines the journey and important steps the team took to make the machine learning models from our dataset. We started off by splitting the data into test and train set. Then we built a pipeline that consisted of scaling, dataset, and model definition code. Then we trained the model, started evaluating the trained models, which can be used for hyperparameter tuning. And after hyperparameter tuning was performed, we re-evaluated the models on the test set. And finally, a final model was chosen. This is a brief summary of important parameters that were used to make models for approach number 1, which used data that was sampled at 20 seconds, and approach number 2, which used data that was aggregated by every hour. After using various algorithms, we documented their performance on the RMSE score as shown in the snapshots here. We found out that random forest regressor tend to perform better on a larger dataset that was sampled at 20 seconds, and gradient boosting regressor performed better on the resampled dataset that aggregated the values every hour from the original dataset. Here is a snapshot on our model's performance before and after performing hyperparameter tuning. One important finding was that the model's performance was not drastically improved by hyperparameter tuning due to the hardware limitations. Due to the large size of our dataset, our team was limited on the hyperparameter tuning. We also realized that model number 1 performed better than model number 2 as indicated by the various scoring parameters. Now that we have looked at the problem and our solution, next we will look at the key findings and the next steps. We have produced a good model that is able to predict percent silica with an accuracy of 93.80% on the large original data set, where the data was sampled at every 20 seconds. We can also see that model number 2 performed poorly on the small resampled data set. The project indeed is a success, and it requires further tuning to improve accuracies of the model. In terms of the next steps, we want to first revisit the problem and consult with the business to better understand the data, its variance, and align on the sampling period. Next, we will need more powerful computers to perform in-depth hyperparameter tuning to find the best parameters that will maximize the model's performance. Then we will also experiment with various ML packages to see which one tends to perform better than the other. Lastly, we want to perform time series forecasting of our features such that the target variable can be predicted ahead of time. For example, predict sensor values based on historical data and run it through our trained model, which will indeed end up predicting the target variable. Thank you for listening in, and please check out our project on GitHub. For your reference, here is an overview of how our model compares to the predicted values versus the actual values from the dataset. Here is a snapshot of the code that was used to come up with the accuracy score for regression models. Thank you.